Okay, so this is the review session for midterm 2 for EGME 308 in spring 2023. Okay, so for our second midterm, there were two main, I would say, kind of big topics that we covered in the class. And so one was vector calculus, and so we did differential vector calculus, then integral vector calculus, and the other was Fourier, which is what we just kind of finished up, right? So I wanted to kind of review both. Okay, so let's start with vector calculus. Right, so let's start with differential vector calculus. Right? Okay, so the main thing with the vector calculus, there are kind of two main things that I wanted you to kind of pick up from the vector calculus section. So, a lot of this hopefully was review. So hopefully you've seen a lot of these things in classes like 250A. But what I really wanted to kind of impress on you guys was, kind of what's the physical intuition, or, what are some physical applications of where you would see a lot of these mathematical tools, right? And so I'm going to skip, all the vector algebra review stuff. And so, dot products, cross products, I'm assuming you guys know how to do that at this point. But let's skip kind of right to the first big topic in differential calculus, which was the gradient. Okay. And so the gradient is a derivative type operator, which you can perform on a multivariate function. Okay. Okay. In particular, what the gradient will do is that for each independent variable in your function, and so for a lot of field stuff, we have functions of x, y, and z. What you're going to do with the gradient is you're going to take a partial derivative of that function in each direction. Okay. And then what it's going to do from there is that it's going to save your result as a vector. Okay. So for example, let's say that we have some field function, and this is a function of x, y, and z. Okay. And so if we were to take the gradient of f, this would be a three element vector. Okay. So we have partial f, partial x, partial f, partial y, and partial f, partial z. Okay. Right. And so to take the gradient, you basically just take your function f, where your function f is going to be a function of all three variables. And so I think the example that we did in the class was f of x, y, z is equal to, this is just one example, 2y cubed plus 4xz plus 3x. Okay, so that's your function. And so to take the gradient, you would take the derivative of this in each direction and then store it in a vector quantity. Okay. Okay, so the gradient has a lot of uses and a lot of applications, and in fact, you're going to see the gradient in a lot of your, mostly thermal fluids courses, and so you'll see it in fluid mechanics if you haven't already, and in heat transfer as well. Okay, and so the first application we went through was the directional derivative, right? Okay. And so the idea with the directional derivative is that when you have functions, or when you have functions that depend on multiple variables, sometimes you're interested in basically what's the rate of change of the function in an arbitrary direction. Okay. Okay. Right. And so, we know how to compute the rate of change in the cardinal direction. So if you want to compute the rate of change in the x direction, you just take partial f, partial x. If you want to take the rate of change in the y direction, you do partial f, partial y. Same thing for the z direction. But, let's say that we want to compute the rate of change in like a diagonal direction, right? So one that doesn't align with with the coordinate axes. And the way you do that is with a directional derivative. And so the formula for this is that you have a vector A. Okay. So this vector A, this represents the direction in which you want to take, or you want to compute the rate of change in. Okay. We're going to take that and we're going to take the dot product with the gradient. Okay. Right. And so in the end, you kind of get a scalar quantity that represents the rate of change in the A direction. Okay. Okay. So that's a pretty straightforward application. Next, let's talk about the direction of maximum increase. So this is the application from the homework. Okay. I guess this is not really an application of the gradient, more so as it's just an interpretation of what the gradient actually represents. Okay. And so remember, the gradient, when you take it of a typical function, you get a vector quantity, right? And so that vector, the vector that the gradient itself points in the direction to, that tells you the direction in which the function is going to increase the most um, in terms of magnitude. Okay. And so we use this a lot in engineering. And so the example that I brought up was heat transfer, right? And so if you take the gradient of the temperature field, and in fact, this was the example that was covered in homework 4 as well, right? So the gradient of the temperature field tells you which direction that the temperature is increasing the most, right? And so if you take the negative of this, then the negative of this is going to be the direction that the temperature is decreasing the fastest, right? And so the way heat transfer works is that heat always goes from high temperatures to low temperatures. And so if you can know, or if you can learn kind of the direction that which the temperature is decreasing the most in an application, that's going to tell you which direction the heat or energy is going to flow in the system. Okay. Okay. So, I'm going through this very quickly because, what's most important, again, like I said, is kind of the physical interpretation of these operators, right? And so, gradients, yes, there's a lot of examples out there on how to compute it, but what we're interested more in is how do we actually use this in engineering? Okay. Okay, so that's the gradient. So now let's talk about the divergence very quickly. Okay. So the divergence of a field is simply going to be, almost like it transforms. It's a derivative operation that transforms a vector field into a scalar field. Okay. And it looks something like this. And so we have the divergence of some vector v is equal to partial vx, partial x, plus partial vy, partial y, plus partial vz, partial z. Okay. Where v, remember v is a vector field. So v has three components, vx, vy, and vz. Okay. Okay, so what the divergence here kind of represents is how much the vector field is kind of spreading out or converging at a given point. Okay. Okay. And so this is mostly used in fluid mechanics, and so you're going to see the divergence appear in conservation of mass applications. Okay. Okay. So I'm not going to say too much more on this just because it kind of takes a bit longer to explain. But definitely check out the our lecture videos on this topic because I discuss it a lot more in detail there, and of course the lecture notes as well. Okay. Okay. So the last piece of differential vector calculus that we went over was the curl. Okay. And so the curl is physically what the curl represents is how much a vector field is swirling in a given place. Okay. And so we have nabla crossed with the V. Okay. And so in order to compute it, you would take kind of this arbitrary or pseudo kind of cross product between these two things. Okay. Okay. So I want to go over this kind of fairly quickly. Not because I don't think it's important, but because I want to get to more of the integral vector calculus stuff, which is where we can actually compute stuff. Okay. But for the curl, the applications for this are going to be mostly in fluid mechanics again, and it's going to be based on cases where you're interested in how much the vector field or how much the fluid field is swirling. Okay. Okay. All right. So with that said, let's go ahead and move on to integral vector calculus. Okay. And this section was all about what are some important theories in vector calculus that involve integrals and how we can interpret them as well. Okay. Okay. And so I'd say there's kind of four main topics here, right? And so there's the idea with line integrals. There's Green's theorem. Okay. Then kind of in parallel to this is we have surface integrals and the corresponding theorem. Okay. Which is the divergence theorem. Okay. And so once again, it's important to kind of know kind of what all these integrals are, and we'll kind of go through them conceptually what they mean soon. But in terms of calculations, I think that's the part that kind of people want to know about. I know we covered in the class and we went over it in quite a bit of detail in terms of how to compute line integrals and how to compute surface integrals. But I will say that kind of in general. a lot of times you don't want to be computing line integrals and surface integrals. Okay. Okay. And the main reason for this is not that it's not that it's bad, and so not that it's bad for you, like it's not going to hurt yourself to do it. They're just a lot more time consuming because you have to spend a lot of time doing things like parameterizing the curve, parameterizing the surface, reparameterizing your integrand and things like that. So, usually it's something that is more trouble than it's worth. Okay. And so what I'm hoping I kind of or kind of the main impression that I hope I left you with from this section is, the fact that, the reason these theorems exist, both the Green's theorem and divergence theorem, okay, they both kind of serve one important purpose, at least in terms of calculation, in terms of calculations, right? And is that they allow us to basically convert line integrals and surface integrals into things that are usually much easier to compute. Okay. Okay. And so that's in terms of calculations. And so if you see a problem on the exam with a line integral or a surface integral, first thing you should see is that first thing you should ask yourself is, can I use one of these integral theorems to convert this into an easier form? And a lot of times that easier form is going to be a lot easier to work with. Okay. Okay. So with that in mind, let's go ahead and kind of review everything really quickly. Okay. So let's go from line integrals first. Okay. And so conceptually, you can think of line integrals as almost like a generalization of a classic 1D integral. Okay. Okay. And so 1D integral looks something like this. So you have an integration from a to b of some function f of x dx. Okay. And in this case, we're integrating along a single, basically a horizontal line. So we're integrating just along the x-axis. Okay. So line integrals, they also perform an integration along a path. It's just that that path can be something arbitrary in 3 dimensions. Okay. Okay. So that's basically all it is. And so, the classic form for the line integral looks something like this. Okay. Okay. And so we have some function which we parameterize in terms of some path r, and then we basically take the dot product between this function and the function's tangent, which is dr. Okay. Okay. And so traditionally, what we use the line integral for, especially in Green's theorem, is we like to see basically how much of a vector field aligns with a certain path. Okay. okay, where our path is given by r of t. Okay, this takes on an even kind of an even more special meaning when the path that we choose is a closed path. Okay. Okay. And so let's review what it means to be a closed path. And so a closed path is nothing more than a path that has the same starting and ending point. Okay. And so essentially the path goes in a circle. So it starts out, it goes around, and it can even do a lot of like a lot of loop-de-loops. It can do a lot of kind of crazy stuff. But in order for it to be closed, it has to come back to the same point, right? So maybe we have something like this, okay? Where this is our starting point, and we progress kind of this way along the path. Okay. Okay. And so we usually indicate a line integral like this along a closed path with a circle on the integral like that. Okay. And this takes an even bigger meaning. And so, if we kind of look back and we look at our kind of our definition for the line integral in terms of seeing how much of a vector field aligns with this path, right? If the path goes in a circle, then our line integral is going to represent how much that vector field kind of also goes in a circle. Okay. Okay. All right. And so we can use this idea, and this is kind of the basis for Green's theorem. And so Green's theorem says that this idea that we have a line integral here that represents how much the vector field goes in a circle. What the Green's theorem says is that we can express this in a different way. Okay? And so what Green's theorem says is that the double integral of the curl of the vector field f, okay, dx dy is equal to the line integral around the closed region of R. Okay, and so we have a closed line integral along the path C of R, our f dot dr. Okay. Okay. And so by taking the curl and then adding up all those curls in that region, we can say that this is also equivalent to the line integral around that same region. Okay. And so this is kind of where we first kind of see this idea that I presented you with, maybe like 10 minutes ago. Okay. And so usually when you have these integral theorems, one side is going to be easier to compute than the other side, right? And more times than not, I would say maybe 75% of the time, this side is going to be easier. Okay. Okay. Usually that's the case. And so if you come across a problem in the exam where, it's asking you to compute this integral, integral like this, right? Maybe you convert it. So maybe you say, let me use Green's theorem. Let me convert this line integral here into an easier form. And then, that'll be easier for you to compute. Okay. Okay. So there's a lot more to Green's theorem, and so I kind of just brushed over all of the important conceptual stuff. But so definitely you want to check that out in the lecture notes, and definitely check that out in our lecture videos as well. Okay, but for now I do want to move on. So just to make sure we have enough time for everything, and so let's talk about surfaces and surface integrals, or I should say surface integrals. Okay. So surface integrals, just like line integrals, are kind of an approximation, or not a generalization of our normal 2D integral. Okay. And so a surface integral is the generalization of a 2D integral where our integration domain is an arbitrary surface in 3D space. Okay. All right, and so the surface can come out of the plane, of course. It can be a closed surface, just like the line integral. So there's a lot to this. Okay. So the general form for a surface integral is we have a double integral, okay, of f of r u and v dot product with the surface normal, which is also a function of u and v. Okay, u and v here are our generalized surface coordinates, and so whenever you have a 2D surface, even in 3 dimensions, you use basically 2 parameters to define it. Okay, and we're going to integrate over those 2. Okay. Okay. And so unlike the line integrals, where line integrals are a little bit annoying to compute, but at least it's still doable. Surface integrals are usually a lot more difficult to compute. Okay. And so oftentimes you're going to want to convert these into a different form to make your life, easier. Okay. But what's most important about the surface integral here is its physical interpretation. And so the surface integral, mostly due to this this part right here where we're taking the dot product. Okay. Remember, the surface integral represents what's known as the flux, or how much a vector field passes through a 2-dimensional surface in space. Okay. Okay. And so if we have kind of our arbitrary surface here, okay. Okay. When I say flux, our vector field F consists of, lots of arrows that kind of go through space, right? And so how much those arrows actually pass through the surface, okay? So in red here, I have the arrows for F, okay? How much those arrows actually pass through the surface can be computed via the surface integral, okay? But again, a lot of times this is a lot pretty difficult to compute, and actually the big bulk of the of our integral vector calculus notes is devoted to computing those things. Okay, a much easier way to compute this is to use the divergence theorem. Okay, and so what the divergence theorem says is that if you have a surface integral in a closed surface, okay, this is equal to a triple integral of the divergence of a vector field, of that same vector field. Okay. Okay. And so believe it or not, a lot of times this quantity on the right is going to be a lot easier to compute, okay? Because remember, what happens when you take the divergence? When you take the divergence of a vector field, you end up with a scalar, right? So this right here is a scalar field, which is much easier to work with, okay? Right. So whenever you see a divergence in an application, you should kind of rejoice because it ends up making things a lot simpler than it is, right? And so even though you have kind of one more integral to compute on that side, that right side ends up being a lot easier to compute most of the time. Okay. And a lot of times your domains are going to be such that it's easier to compute those than not. Okay. Okay. So I have lots of examples of this in the notes, so please make sure to check it out. And so, in this kind of short video right here, I can only cover so much, but I at least want to give you kind of hints of kind of where to look in the notes for kind of some more important concepts. But definitely look that up because you don't want to be computing a surface integral on the exam because that's going to take way too long. Okay, so now let's move on to the next big thing, which is Fourier. Okay, and so we start with the Fourier series. Okay. And this kind of goes for both, Fourier series and Fourier transforms. And so, we're kind of making a big shift in topics here. Okay. And so the whole idea behind Fourier is that, it's all about kind of representing functions in a different form that involves frequency. Okay. Okay. I should say it's not just about frequency, it's about amplitude and frequency. Okay. And so remember, the when we talked about Fourier, we talked a lot about its parallels with the concept of sound, right? As we talked about volume and sound, we talked about pitch and sound, right? So you definitely want to review those concepts and how they connect to Fourier, because those are kind of important to know. And I think it kind of gives you a good physical intuition for, what Fourier actually kind of represents. Okay. But let's go ahead and kind of jump ahead to the calculations. Okay. And so when we're talking about Fourier series in particular, right? In Fourier series, what we're looking to do is we're looking to basically represent a periodic function as a summation of sine and cosine functions. Okay. And so our main function, our main formulas are the following. And so if you have some function f of t, okay, so f of t is your periodic function, right? What we can say is this is equal to a naught plus summation from n is equal to 1 to infinity, okay, of an cosine of n pi over L times t plus bn sine of n pi over L times t. Okay. Okay, so that's the representation for the function. Okay. And so the important quantity here, of course, is L. And so by L, remember, is the half period length. Okay. And so remember, you can only apply Fourier series to periodic functions. And so every periodic function has a certain amount of time that it takes to repeat, repeat itself. Okay. And so L is just simply half of that period. Okay. All right. And so, of course, the main things that you're computing here of a Fourier series are the values for the coefficients. And so we have the A naught coefficient, we have the AN coefficient, and the BN coefficient. Okay, so let's go ahead and write down our formulas for those. And so for A naught, the formula for this is 1 over 2L integral from minus L to L of f of t dt. Okay. AN is equal to 1 over L integral from minus L to L. Okay, f of t cosine of n pi over L times t dt. Okay. And then we have Bn. Bn is equal to 1 over L integral from minus L to L of f of t sine of n pi over L times t dt. Okay. Okay. And so if a question is going to ask you to compute the Fourier series expansion of a given function, then essentially you'd be doing kind of two things. So first you would compute the values for the coefficients. And so you would compute A0, AN, and BN. And then what you would do from there is then you would plug those in to the expansion up here. Okay. And so a lot of people, when you're doing a Fourier series problem, most people will get an expression or they'll get an answer for the coefficients, but then they won't plug it in. And so, the question is not complete or the problem's not complete until you actually plug it back into this expansion up here. Okay. Okay. All right. So of course, if you're doing this kind of for an arbitrary function, an arbitrary problem, it's a lot of work to do all these computations just because there's a lot of coefficients and there is a lot of integration to do, right? The good news is that we can simplify our problem if our function f is an even or an odd function. Okay. Okay. And so remember, we talked about in class what an even and odd function is. So an even function is nothing more than just it's symmetric across the vertical axis. Okay. Okay. Another way you can compute it, or another way you can see if this is true, is by doing the mathematical test. Okay. And so the mathematical test is that if you compute your function, okay, and you evaluate it at minus t, that should give you the same thing as f of t. Okay. So this may be a little bit easier to see for some people than the visual look. And so let me give you an example. Okay. So the very classic kind of even function is a quadratic function, so t squared. Okay. Okay, so we have f of t is equal to t squared. Let's test out f of minus t. Okay, and so we plug in minus t into this equation here. So we have minus t squared. Okay. If we break this apart, this gives us minus 1 squared times t squared, right? So minus 1 squared here is just 1, okay? And so what we get is f of minus t is equal to t squared, okay? So since these two are the same, okay, so we went ahead and plugged in minus t into the equation. We ended up with the same thing. We know that this is an even function, okay? Okay. All right, so an odd function is symmetric across a diagonal line. Okay. But the easier way to kind of figure this out is to check the function itself. And so what you're going to do, you're going to take the same function, plug in minus t, and what you should get is minus f of t. Okay. Okay, so let me give you an example with the piecewise function, which is kind of more likely kind of what you're going to receive in the exam. Okay. And so let's take one example from the homework. And so for the homework, we had this function here. So we have minus 4 minus t or plus t. Oh no, minus 4 plus minus t. Sorry. Okay. For 0 is less than t is less than, or sorry, from minus 4 less than t less than 0. Okay. And then we had 4 minus t for 0 is less than t less than 4. Okay. Okay. So let's plug in f of minus t. Okay. And so if we plug in f of minus t here, we get minus 4 plus t, okay, and 4 plus t. Okay. Okay. So what I'm going to do is I'm going to factor out a minus 1 here. And so we factor out a minus 1, we get minus 1 times 4 minus t. Okay. Then down here we have a minus 1, and we have a minus 4 minus t. Okay. I'm getting my t's and 4's mixed up. Okay. And so if you look at this, and look at this up here, right? You can see that they're opposites of each other, right? When we factor out that minus 1. And so when we plugged in f of minus t, we get kind of just the opposite function of what we obtain. Okay. An easier example of this is f of t is equal to t cubed. Okay, so we plug in f of minus t here. We have minus t cubed. We end up with minus t cubed. Okay. And so that's kind of an example if you end up with just kind of the opposite of the function. Okay. Okay. And so for even functions, you can make the simplification that Bn is just going to be equal to 0. Okay. And then for odd functions, you can make the simplification that a0 and an is equal to 0. Okay. So that's definitely something you want to check, because remember, on the exam, you're going to have kind of a very limited amount of time. And so you want to make basically any time where you can you can make a simplification, that's always going to help. Okay. Okay. And so the last thing I want to go over with Fourier, or at least Fourier series, is half range expansions. Okay. And so with half range expansions, usually we're given what the function looks like for an entire period, right? And so that's kind of our traditional Fourier series. For half range expansions, sometimes we're only given the function definition for half of a period. Okay. Okay. And so in other words, these functions are only defined from 0 to L, right? And so, in these cases, we can still compute a Fourier series expansion, but we have to make an assumption in terms of, what the function looks like on the other side of the vertical axis. Okay. Okay. And so there are two half-range expansions that we can always do. So we can always assume that the function is either going to be an even function, or an odd function. Okay. Okay. And so for an even half-range expansion, you're only going to compute the A0 and AN. Okay. And so for an odd half-range expansion, you're only going to compute the Bn. Okay. And all this is just based on the assumption of, what the function is going to look like on the other side. Okay. All right. And also, just also be aware. So, check back in your notes again. I do want to move on to Fourier transforms just to keep this video under an hour. But the formulas for the half-range expansions are slightly different because we only integrate from 0 to L. Okay. Basically, you would take the same formulas that you had up here. Okay. You would change the bottom integration here to 0. Okay, so this is for half-range expansions only. Okay, and so you can see that I've changed all the lower integration bounds here to 0 for all three. And then what you're going to do is you're going to multiply it by 2 out in front. Okay, so it's slightly different equation just because remember you're assuming that the function is going to look either even or odd on the other side, and so you only have to integrate it by half the period. Okay, so it's just kind of something to keep in mind when you're doing these Fourier or half-range expansions. Okay. Okay. All right. And so the last section that we went over, this is kind of the most recent thing, is the Fourier integral and the Fourier transform. Okay. Okay. So let's go over the Fourier integral first. And so the Fourier integral is basically a continuous, you can almost think of it as like a continuous form of the Fourier series. Okay. Okay. Because remember the Fourier series, we have an infinite summation there, but because our summation has an integer value n, we only basically examine, or we basically only hit discrete values of frequency along the series. Okay. Okay. So I'll just show you really quickly with the cosine term, but it applies for the sine as well, right? And so for the Fourier series, that's the ugliest summation symbol I've ever written. Okay. And so remember, we're summing from n is equal to 1 to infinity of cosine of n pi over L t. Okay. And so since n is an integer, right? Right, it's going to count up from 1 to 2 to 3 and so on and so forth. Okay. That means this quantity right here is only going to hit discrete values of frequency. It's never going to be a continuous function, right? But oftentimes, we want to look at every single frequency, right? And so it's not just the discrete values. And so what we did, the first thing we did in this chapter here was we took our Fourier series and we kind of generalized it for a continuous function. Okay, and so that's what gave us the Fourier integral. And so the Fourier integral and the Fourier series are pretty much the same thing. It's just that instead of computing discrete coefficients, we have a function of frequency instead. Okay. Okay. And so let me write out the Fourier integral first. And so the Fourier integral is basically saying that we have a function. If we have a function f of t, we could represent this in the frequency domain as an integral from 0 to infinity of some function a of omega times cosine omega t plus another function b of omega times sine omega t. Okay. And we're integrating over omega here. Okay. And our two functions, a of omega and b of omega, are given by the following. Okay. So a of omega is equal to 1 over pi integral from minus infinity to infinity of our function f of t cosine of omega t dt. Okay. And b of omega is equal to 1 over pi integral from minus infinity to infinity of f of t sine omega t dt. Okay. So that's the Fourier integral. Okay. And so with the Fourier integral, we got a lot of really interesting concepts. Okay. And so the first thing is the Gibbs phenomenon. Okay. And so remember, one interesting thing about the Fourier transforms and the Fourier integrals is that, we're not able to, Fourier does not, I should say, Fourier does not really recognize the existence of function discontinuities. Okay? And so when you have a discontinuity in your function, what Fourier is going to do is it's going to try to smooth it out. Okay. But because of this, some interesting things happen. Okay. Right. And so if you do have a function with the discontinuity, and so let's say that we have something that looks like this. Okay. And so in black right here, I've written the function f of t. Okay. And we have two discontinuities. And so we have a jump on the left-hand side as we go from the bottom to the top. And on the right-hand side, we have a jump from the top to the bottom. And those are considered discontinuities because we have vertical lines. Okay. If you represent this with Fourier, right? And so if you have either a Fourier series representation or a Fourier integral, what's going to happen is something like this. Okay. Okay. And so you're going to have these kind of like bunny ears or overshoots in the function. Okay. And so these overshoots are known as the Gibbs phenomenon. Okay. And they're unavoidable. And so basically they're always going to be there kind of no matter what. Okay. But they are basically there. And the reason they're there is because of Fourier does not, it basically, has to smooth out these discontinuities, okay? And a lot of times that's actually something beneficial. And so a lot of times, you don't want to have these discontinuities in your function. And so having something that's going to smooth them out is valuable, okay? Okay, and so with that, let's go ahead and move on to the actual Fourier transform. Okay. And so the Fourier transform here, this is kind of the official way, or kind of the official way to take a function in the time domain and transform it into a function into the frequency domain. Okay. Okay. And so this function, f of omega, is equal to integral from minus infinity to infinity of f of t e to the minus I omega t dt. Okay. And so, of course, this is the complex form for the Fourier transform. And so, there is a sine and cosine form as well. But when people think of the Fourier transform, this is usually the one that is that's mentioned. Okay. Okay. And so the last thing I want to mention here of kind of physical significance is the power spectrum. Okay. And so after you compute the Fourier transform, what you're going to have is a function of omega, right? And so if you plot this function, or I guess technically you're plotting the square of the function, so you're taking f of omega squared, it's going to give you a what's known as the power spectrum. Okay. Okay. And so what the power spectrum tells you is that it tells you basically how much energy in the original function, or how much amplitude there is in the original function associated with the different frequencies. Okay. Okay. And so we have situations that, a typical power spectrum might look something like this. Okay. And so on the x-axis, or the horizontal axis, we'll have frequency. And on the vertical axis, we'll have the Fourier transform squared. Okay. And you might have some things that look like this. Right. So oftentimes you're going to have some frequencies that kind of stand out the most. And so they're going to have more power than the rest. Right. And so all this tells you is that, in our original function, these frequencies, I was highlighting with my mouse and realized you can't see my mouse, right? These frequencies are going to be the most dominant frequencies in your signal. And oftentimes, if you're doing signal processing, if you're doing signal smoothing, if you're trying to find like frequency response, if you're trying to find the natural frequency of a system, these are often really interesting to know and really important to know for your application. Okay. Okay, all right. So that was a lot of stuff, and I will say that I did skip a lot just because we've covered just a lot of information since the first midterm, and so this, I think, for this video, I think it did a pretty good job of giving kind of a general overview of everything, but there are a lot of details and a lot of concepts that I did kind of gloss over or just kind of mention briefly, and so I do encourage you. So if you are using this video to study, don't make sure this video is not the only thing that you're using. And so please review all the other materials, the lecture notes, the lecture recordings, the homework problems, the homework solutions. Use the study guide. Please use everything at your disposal, because this section, at least for me, I think it went by pretty quickly, but it was very dense in terms of information. So we covered a lot. right? And so make sure you cover all those bases that we didn't really have time to cover here, especially example problems, because we didn't really have time to do example problems in this review video. So make sure you do that in your study. Okay. All right, so I'll go ahead and close this here. So best of luck with your studying. If you have any other questions about anything, please let me know. I'm always available. I'll try to be as available as I can until the midterm exam on Thursday. And so, yeah, have a good weekend and best of luck studying.